So yes, so today I will talk about character sheaves for a Parahoric subgroup. I guess I call it generic character sheaves for Parahoric subgroups. This is all joint with Roman Bezrukavnikov. So allow me first to begin with a story that probably many of you in this room know. But let me tell you just something very briefly about representations of finite groups of Lie type. And I'm going to call this G0. And so this story is relatively well understood. And let me tell you a little piece of it. Essentially, the irreducible. So also all of my representations are over C or over QL bar. So I won't say that again. The irreducible representations of G naught here are essentially, roughly speaking, parameterized by the following kind of simple meaning easy data. Meaning you take a maximal torus inside your G together with a character theta of the FQ points of your torus here. And basically there's a recipe from this side to the irreducible representations of G naught. And so probably also most of you know that this is kind of a lie. So let me put like this. And the reason it's a lie is that okay, let me say more before I say something about the lie. Okay, so how does this recipe go? Well, from such a pair, what I first do is I look at this maximal torus, and with this maximal torus, I can pick a Borel subgroup that contains this maximal torus. Now, this Borel subgroup may not be defined over FQ; it's defined over FQ bar. So probably that should be in the notation, but let me not put it in the notation on the board. And then I'll throughout the talk, I'll also write U for the unipotent radical of a Borel. And so what happens here is that attached to this is what's called a Deligne-Lusztig variety. I'll just call it X. It's basically the pre-image of this U under the Lang map. And the important thing about this X is that it comes with two commuting actions, one by G naught and the other by what I'll call T naught, which is just the FQ points of this T right here. Now, of course, T naught sits inside G naught. So if you have a G naught action, then you have a T naught action. But the point here is that there's a different action that commutes with the entire G naught action. And so how do I get a representation of this? Well, I'll take the cohomology of this with QL bar coefficients. And then now I have this extra piece of data. Okay, well, let me also put -1 to the I, so I don't care about which actual degree appears in. This theta right here is some extra piece of information that I need to stick into my description on the right. And so how I do that is I say, well, I have this T naught action that commutes with all of this. If I specify how this T naught action works, then I'll be left with a G naught representation. And so when I specify that T naught acts by theta, I put a little theta over here. And this representation I will call RTG theta. So when someone says RTG theta, oftentimes this is the font of the RTG theta. And so here's the lie, is that this RTG theta is an irreducible of G naught if and only if. Okay, hang on. I will die if I don't take care of this now. Okay. So it's an irreducible if and only if theta is in general position. Okay. So basically all we will consider in this talk is things like when theta is in general position. So there's other stuff. It's a little bit more complicated. Let's not worry about it. So in fact, RTG theta can be characterized in the following elementary way. And so let me write down the theorem. Like this. So let theta be in from your T naught to C star or Q bar be in general position. Then there exists a unique, irreducible such that the character of this representation is up to a sign. So this dot is up to a sign. The sign is the same for all the gammas in this locus. For all gamma regular semi-simple inside G naught. Okay, so it's possible, for example, for your gamma to not be conjugate to any element inside your T naught. That's taken care of by this W, which is not in the notation here. But then you, instead of the actual W, the Weil group, you take, all the things that take your T naught into the connected centralizer of gamma, in which case that's 0 and the character vanishes. Okay, so I just write it like this. Just know that you need a little bit more words to make it completely precise. Okay, so let me attribute this. So existence is due to Deligne-Lusztig. And what is this pi? Well, this pi is this RTG theta. So the pi is the RTG theta. Oh, okay. Did I start at 11:15? Yeah, okay. So existence is due to Deligne-Lusztig, and uniqueness is due to a theorem of Lusztig. But oh my gosh, it requires an additional assumption, which is that Q has to be sufficiently large. Q is this Q right here. Okay, so let's not worry too much about Q because this is kind of just some context for the point of the talk. Okay, so note here that even though the character formula for this RTG theta is very simple on regular semi-simple elements, it's not so simple outside of this locus. So this is not so easy outside G naught. I'll call it reg, but know that it's actually RSS. Yeah, so it's not so easy. It's not extremely hard. It's known. It's known by Deligne-Lusztig. And so this formula here, the existence of this formula is a super, super special case of Deligne-Lusztig's character formula for RTG theta. But this note is important for us. So remember this note. Okay. So next, let me tell you about some representations of what I'll call GX0, which is a Parahoric subgroup. Okay, and so the context for this is I start with G, a connected reductive group, over F, a non-Archimedean local field. This is allowed to be characteristic 0 or characteristic P. That doesn't matter for us. I'm going to take P inside G to be an unramified maximal torus. It does not have to be elliptic. It just has to be a maximal torus. And the same situation as up there. And I'm going to take X to be a point inside the rational building intersected with the apartment of this T. Okay, and so for instance, if T is elliptic, then there's only one thing in this intersection. But if T is not elliptic, then there's lots of things. Okay, so let me write the theorem first, and then so this should be, you should think it's completely parallel to the above situation. So let theta on TO, yeah, okay. Well, I can just think of TO to be the intersection of T with this GX0. So I guess I should say this data here just allows me to consider a subgroup of G of F. This is my Parahoric here. Okay, so I'm gonna let theta be a smooth and sufficiently generic character of this TO. And sufficiently generic has it's a break. I mean, this has two conditions. One condition is the analog of the above in general position. And I didn't say it before, but in general position simply means that the stabilizer of theta under the action of the wild group is trivial. So we have that, but we have an additional genericity property, which in some contexts is called G generic. So I'll write this here without explaining further. Just know that it's far from being trivial. Then there exists a unique, irreducible irrep of GX0 such that, I guess I should probably say smooth here, but okay, such that the character of this is, again, up to a sign given by exactly the same formula as above for all gamma. Okay, so we don't have a notion of regular semisimple anymore here. However, we can if we replace the notion of regular semisimple over there with unramified very regular, then we obtain the same simple formula. So let me define what unramified very regular means. So gamma is an element inside this GX0, which means it's an element inside this G of F. So the first thing I'll require of gamma is that it's regular semisimple inside the p-adic group. And then the second thing that I will require is that I will actually just verbally say this, is that the connected centralizer of this gamma is an unramified torus inside your p-adic group. And the second thing is that basically if you evaluate roots on this gamma, then it's always non-trivial mod p. And so how you should think of it is that this gamma is like is sitting inside this GX0, which is kind of a fattening of my G naught up there. And if you quotient to G naught, then you get something regular semisimple inside G naught. So it's like the head of it is regular semisimple. Okay, but it's allowed to be fattened by other stuff. So the smoothness implies that we can pass to some finite quotients, can pass to a finite quotient, which I'll call TR cross GR. This is a finite quotient of TO cross GX0. Okay, so now, so as before, the existence and the uniqueness, these are due to different people. So existence is due to work that I did with Alex Ivanov, who's in the audience now. And the way that we show the existence is by studying a variety that's very close, that's basically completely analogous to the Deligne-Lusztig variety X that I introduced over there. And basically for the same geometric reasons that control the simplicity of the character formula on the regular semisimple elements up there, over here, unramified very regularity controls this, determines this simplicity here. And the essential reason is that the fixed points under such a gamma is 0-dimensional. Up there, the fixed point of x under any regular semi-simple element is 0-dimensional. So the character is then easy to calculate. Okay. And the uniqueness of this is due to myself and is joint work with Masao Oi. Okay. So, right. So I said already that there's this, yeah. Okay. So the existence part is to construct analog of x, let's call it xr, with the same essential property as above, which is that this has an action, has commuting actions by gr and tr, and therefore, by considering the cohomology of this and looking at the part in this cohomology where the tr acts by this sufficiently generic character, then I get an irreducible representation of gr here. And here I will again call this something like our g theta, but now we have this r, little r floating around as well. So this one is rtr gr theta. Okay, so like this. Okay, and so note again, oh my gosh, is this the character of r tr gr theta is not so easy outside gr vreg, even though it is determined by the values on this easy part. Okay. Okay, so let me make a comment and then I'll start talking about character sheaves. Okay, so just a remark. As you might say, okay, well, oh my gosh, what's the relation to p-adic groups, maybe representations of p-adic groups is the following thing. So let's say if T is elliptic, then the following thing. So one, then the compact induction, actually, let's do this. Then the compact induction of possibly extended by center r tr theta is irreducible and therefore supercuspidal. So when r is equal to 0, this is a theorem of Moyen-Prasad. When r is positive, then this is actually not known in complete generality, but most of the time, yes, is right. R in the division algebra case, this is something that I studied some years ago. For the remaining inner forms of GLN, this is something that I worked on with Alex, and in general, this is, maybe I'll put without the F here. This is joint with Masao Oi, except in the general case, the technique that Oi and I use requires Q to be sufficiently large. This is alarming. Okay, I need to learn. Okay, so from now on, I'll actually denote GR for an FQ scheme that's associated to this this R quotient. I wrote quotation marks just because on that side, technically I didn't actually have this notation. So view it as an FQ bar scheme. And then I'll remember the FQ structure by specifying a Frobenius map from GR to itself. Okay. So this notation is also set for G0. And so next, let me tell you about character sheaves for G0. Remember, G0 is now this FQ bar algebraic group. So here, okay, actually, this is a natural stopping point to ask for questions. Any questions at this point? Yeah. Yeah, it's so far away. GR is a finite quotient of the Parahoric.
Yes, and then when you do R, GR, is that a representation of GR or of all of G?
Both. So if you have a representation of GR, then you can just pull it back to a representation of GX0. And then to get a representation of, I think what you mean by G is the p-adic group, you compactly induce. So that's this comment here. Okay. Okay, I think this is being locally answered. So consider what's called the Grothendieck-Springer resolution. I'll define it for you. This is, I'll call it G0 tilde. And this is given by the following thing. I take all pairs, G, comma, B0, B0, such that this thing here is inside B0. Okay, so this is a pretty well studied thing. Yeah. G0, yeah, so G0 will just be a connected reductive group over a finite field. Yeah. And then for GR, R positive, then we have to take a deeper quotient. Okay, so the Grothendieck-Springer resolution comes with two maps. I mean, probably other maps too, but here are the two that I care about. One is called F and one is called pi. So this map F goes to T0. So this notation goes for all the letters over there. Instead of boldface, I just write regular. So this map here is given by taking this pair and mapping it to the projection of this H inverse GH onto this T0 quotient of B0. And this map over here is just given by, oopsies, by projecting onto the first coordinate. Okay. Okay. And so this is kind of the main diagram that happens to generate your first class of character sheaves. And those are that's the class that we'll care about. So lucky for us. Okay. So let me write here. Why does considering such a thing generate for us a bunch of perverse sheaves? Well, the key is that this map pi is proper and small. I don't need to define proper, but I'll tell you what small means. Small means basically that the locus of things in G0, where the fiber is large, that locus is not too large. So I'll write down. There's a lot of R's around. I'm going to actually change this to an N. Okay. So that's what small means. And basically it's pretty, by standard arguments, what this then tells us is that the push forward is isomorphic to the intermediate extension of its restriction to the regular semi-simple part. Which recall I'm going to write for reg as G naught sub reg. Okay. Okay, so what we can do is restrict this entire diagram to G reg, and something quite nice happens. It's the following thing, is that if we restrict on reg, the restriction of the yes, A, what? Curly L. Oh, yeah, great. Okay, good point. For L, a multiplicative local system on T naught. Okay, so on this regular part, if I restrict this entire diagram, then what do I get? Well, formally, I'll just put reg everywhere. G naught reg, T naught. Yeah. Oh, yeah, I see. How do I do this again? Oh, okay. Yeah, okay. Yeah, better is to do I have, okay, I put in purple this correction to put a purple here on here. Yeah. Does that? What? Yeah, so that was this comment here. From now on, yeah, this one. Yeah. Okay. So on the regular part, what does the we have a special thing that happens, is that on the regular part, this Grothendieck-Springer resolution can be described without the choosing this B naught. It can just be described in with T naught. And so this thing is isomorphic to the set of all things like this, such that H inverse G, H inside T naught, and G is inside G naught reg. And what this allows us to say is, well, suppose I chose my T naught so that it's stable under this Frobenius. My choice, it may not be possible to choose a B naught that's stable under that choice of Frobenius, but now I don't have to worry about it because I know that this push-pull is isomorphic to the intermediate extension of the restriction to this part that's independent of the choice of B naught. And so that's the content there. And so, yeah. Yeah, so this is, I think I cannot remind you what the intermediate extension is, but this is it's characterized by what's happening here. Yeah. Okay, so a key here is that this pi map over here is a little bit complicated, but the pi map over here is very easy. The pi map over here, which I'll call pi reg, F reg, this is étale with Galois group, just given by the Weil group. Okay, and so here's a theorem of Lusztig. Oh my gosh, okay. Theorem of Lusztig is let L be a multiplicative local system on T naught, which is in general position. So what in general position allows me to say is, since this push forward is simply an étale map with Galois group W, this guarantees for me that the push forward on the regular part is going to be irreducible or simple. And so this is what I have. I'll first write down what I already said over here, which is that this push-pull is the same as the intermediate extension on the regular part. And L reg, I simply mean the restriction of this local system L to the regular part. Second part of this theorem is that this push-pull is a simple perverse sheaf which is going to be F equivariant if L is. And that's because of the comment I mentioned before, that we have this nice isomorphism that allows us to forget about this choice of B naught. Okay, and so when I have a situation where I have F equivariance, then the natural thing to me to next consider is the associated trace-of-Frobenius function. So what is that trace-of-Frobenius function? Well, ideally, that should agree with something that we know in classical territory, where classical means something in terms of actual representations, not fancy things like sheaves. And we talked about that over here. And so, in fact, that's the statement here. The trace-of-Frobenius function agrees with Deligne-Lusztig induction. Deligne-Lusztig induction. So in other words, if I take the trace-of-Frobenius on this L here, and I take RTG of that thing, I will get the trace-of-Frobenius of this new fancy simple perverse sheaf. Okay, any questions about this? Oh, yes. Okay. Yeah. Okay. Okay, so oh, actually I wanted to write one more thing down. Okay, so I basically explained how to prove A and B on this board over here. The proof of C is some other kind of beast. You have to construct yet another description of this push-pull of this perverse sheaf in order to make such a comparison. So I'll say a little bit more about this later in the talk. So it's slightly unfair to put it all in one theorem, but that's the way I'll do it. So here is essentially a direct quote from Lusztig. I forget which paper, which is saying that the not so easiness that I mentioned of the character of this RTG theta outside G naught reg, this is in fact controlled by a geometric phenomena. The geometric phenomenon being intermediate extension. That can be what? That's the content of this theorem. Is controlled. Oh, maybe I say the point. Here. Is controlled by a geometric phenomena. Namely intermediate extension. Okay, so given the structure of the talk, then the natural thing to ask is whether in the case that R is positive over here, when I also have the same note that it's not so easy outside the very regular locus, is it still true that the stuff outside is controlled by a geometric, by also intermediate extension? And that is the main theorem. Spoiler, I guess. But let me now slowly give you the details of that. Okay. While I erase, please ask any questions that you might have. What? So if L is not in general position, it will still be a perverse sheaf, but it will not be simple. Huh? C is, I'm a little bit worried. somehow when I'm going through the main points of the argument, I think C is also true. However, what is not true is now this RTG theta can consist of multiple irreducibles inside. And this non-simple perverse sheaf will also consist of several simple summands. The trace of Frobenius of those will not match the trace of the things. But I think on the whole RTG theta, you still have this. Yeah, and so that's part of a somewhat complicated story. I think that's what we call okay, I forget what we call it. So let me was there another noise? Okay. Were you going to supply what we call it?
No, that's something.
Oh, okay. Okay. So okay, now what I want to do is do everything over there, but now over GR. So I'm going to again write basically a mirror of what I wrote over there, the Grothendieck-Springer resolution, and now just stick an R everywhere. This is TR now. This is now GR. This is pi. And again, I'll write this. This is all pairs, such that H inverse GH is inside BR. And again, this map is just projection to the first coordinate, and this is given by the projection to the torus part of H inverse GH. Okay. So here's a conjecture. I don't remember exactly what year, but maybe 20 or 30 years ago. If L is sufficiently generic, TR, then the push-pull is simple and perverse.
Sufficiently generic. So all the position has one step.
Yes, that's right. So that's what I wrote before. So that that sufficiently generic has two components. It first has to be in general position, and the second one has to be so-called G generic, and G generic is equivalent to what you just said. Yes, yes. Conjecture is also stated like this. Yes, I will say something about those later. Yes, this is not the full class of all in general position local systems on TR. That's correct. However, the conjecture is only that for the sufficiently generic ones, this thing is simple and perverse. Okay, so over there, everything that was true is because pi is proper and small. And the essential difficulty here is that pi is neither proper nor small. Okay, so it's kind of bad, right? And so so here are two possible ways to try to attack the conjecture. And then later I'll say the third way that we're actually able to make work. So the first thing is that The first possible thing is suggested by Lustig. And his suggestion is, well, maybe this one is too difficult to compute. So I'm first going to compute the simple perversity of some other complex, and then separately prove that that complex is the same as this complex. So to move the calculation to a different complex. This suggestion is actually in a special case of the TR and GR that we're considering, but let me not tell you all of those adjectives. So the isomorphism between Lustig's suggested alternative complex is true. This is true for all R, and this is proved by Dong-Kwan Kim, who was a student of Lustig's. So we know now that these two things are isomorphic, and now the question is whether this other complex can be proven to be give you something that's simple and perverse. And this other thing, complex, is simple and perverse for R equals to 2 and R equals to 4, and maybe some condition on P. I think maybe P bigger than R, but yeah, so and this is due to Lustig. But Lustig told me that he couldn't do any other cases because for higher even numbers, the computation became too cumbersome, couldn't do it. And for odd numbers, he just didn't know how. So that's one way that one could try to proceed. Another way to try to proceed would be, okay, well, we have something that's neither smooth nor proper. Maybe we're happier if we at least have smoothness. Oh, sorry, neither proper nor small. Maybe we're happier if we at least have the properness, and then we can deal separately with the non-smallness. And so that's the second thing that one could do. Maybe one can construct some nice compactification. I'll put a bar up here. Does this exist such that can control the non-smallness separately? And for example, what you could try to do is to construct some nice compactification of this such that the J lower shriek of the sheaf that you want is the same as the J lower star of the thing you want. And then you separately control the non-smallness. And we tried this for like 2 years, and it didn't. We couldn't figure it out. Not to say it doesn't exist, but we just couldn't figure it out. So the approach that we in the end took, another approach, the approach we could actually do, is to kind of change our perspective, mildly change our perspective, which is that instead of working with this L by L in some sense, study the functor given by this. This is a functor that goes from equivariant sheaves on TR to equivariant sheaves on GR. Okay, so let me state the theorem now. This is old, okay. Yeah, then we don't know how to prove that it's simple and perverse. Oh yeah. So the question was, what happens if L is not sufficiently generic? And what I said is, well, so if L is not in general position, then who asked the question? Oh, you did. Okay, so I might as well look at you. If L is not in general position, then it's unlikely that this thing will end up being simple. And if it's not, it doesn't have the other genericity assumption, then we don't know how to show that it's perverse. Okay, so okay, so here I always start with L, a multiplicative local system on P not sufficiently generic. Yes, there was. Oh, thank you. Yep. PR sufficiently generic. So the first part of the theorem is that Lustig's conjecture is true. So very happy. The second part of the theorem answers the R version of the R analog of this quote right here. And basically more or less follows from the conjecture being true. So this is still the intermediate extension of now not the restriction to the regular semisimple locus, but to the very regular locus of that diagram over there, B reg of L B reg. And so you'll note that on the right-hand side, we kind of used this description for reg to get the simple perversity statement. But here it's kind of in the opposite direction. Okay. And then part C is that this over here, I mentioned that in order to do the comparison to Deligne-Lusztig induction, you need to construct yet another description of this push-pull. That other description also has an analog in this setting. It's a little trickier to prove, basically because of some non-conjugacy situation. I mean, and for connected reductive groups, all the Borels are conjugate, but the analog of Borel over here will not always, you can find two that are not conjugate, and that creates some complications. But these are, one can hurdle over these things. And once again, obtain that the trace-of-Frobenius agrees with now not classical Deligne-Lusztig induction, but this kind of deeper Parahoric Deligne-Lusztig induction. So, in particular, Lustig's quote can still be applied over here, which is that the not so easiness of the character values of R TR GR theta is controlled by intermediate extension from the easy locus, which over here was this unramified very regular locus. Okay. Yeah. Okay. So this thing has another description. This is simply parabolic induction. And so for when you define parabolic induction, it's obvious that it lands in here because the last step is to take an averaging. Then separately, you can consider by unwinding the definition of what that averaging process looked like, it's actually isomorphic to this thing here. So I think how I think of it is that this thing basically tells you that you have a nice behavior with respect to GR conjugacy. This the fact that you pulled back and pushed from here. Okay. So, what time did I start? 15, right? So I end at 15 again. Okay. So, I was going to say something about this C here, but I'm going to skip that now. Or I'll just say it verbally, is that, so this trace of Frobenius agreeing with Parahoric, Deligne-Lusztig, and it doesn't exactly on the nose, you have to have a constant out in the front, and that constant can then be calculated actually by simply calculating the two sides on very regular elements. And so this thing with things on very regular part being easy to calculate comes and hits us in the face again. Okay, so let me finish by telling you about the proof of theorem A. Oh yeah, actually the additional thing is that Lusztig's conjecture was just to go from TR to GR, but in fact we can go from there's a notion of genericity that you can put on local systems on sheaves of Levy, let's call it LR for Levy, and we can also prove that the analog of this push-pull here also preserves simplicity and perversity. So that would be like the general parabolic induction statement. And so that's how one can attack then cases where you don't actually have something that's as generic as what's required in this conjecture. So in particular, attached to some generic data, you can also obtain a simple perverse sheaf, and that's a quite general statement. Okay, so proof of A. The proof of A comes down to the following theorem, which is so. Yeah. So let L psi be a sufficiently generic multiplicative local system on not the full TR, but just the deepest part of TR, the part that's actually controlling this G genericity part. So I'm going to call this T for the deepest part of TR, and then set, this is an L, set script L to be this push-pull of that. So the first thing is that it turns out that both of these, this thing lies inside the TR, and is an idempotent inside here. And this lies inside this category and is an idempotent with respect to, both of them idempotent with respect to convolution. And so what I can consider is now the image of like all things in here that came from taking convolution with something in here, and same with over here. So the statement is then this functor here induces a T exact equivalence of categories, hats, compatible. Oh, maybe I say like this. Okay, closed under taking subquotients so that pi of a simple perverse thing is simple perverse. Okay, so that's the theorem that gives us A. And so in fact, we work with this kind of thing, not only for perverse L, but for any L inside this subcategory of equivariant sheaves. Oh, I see myself all of a sudden. Alarming. Yeah, okay. So let me tell you about the proof of this theorem now. Is the following thing. Okay, so the first thing, of course, is to prove that it's an equivalence. And actually, to prove it's an equivalence already uses in a serious way the genericity property. So without the genericity, basically we cannot control actually what happens here. So already need the genericity statement. Okay, so we want this thing to be T exact, right? So we need some way to be T exact. So what turns out to happen is that, well, there's actually another way that I can get from here to here, which is instead of taking upper star and lower shriek, I can reverse them, take upper shriek and lower star. And it gives me the same functor up to shift. So can do high or shriek, upper star instead. And up to a shift, this is actually isomorphic to the one that we've been considering all along, at least on this locus, so on this special part. So the inverse of this here is given by parabolic restriction, which I will call res lower shriek. And same with this, is given by res lower star. And what is res? Res goes like this. I take, res is going to go in the other direction. So I say something that's on GR, I'm going to pull it back to my BR, and then I'm going to push to my TR. That's parabolic restriction. Now, doing that is the same thing as doing a push first to this quotient by UR, the unipotent part, and then pulling back to BR quotient by UR, which is isomorphic to my UR. So basically what this is telling me is that restriction is the same thing as pushing first and then pulling back to the locus I want. And we get lucky here. Here's a point where we get lucky. Is that because we're only on this generic part, only on this generic part of the equivariant sheaves on GR, it turns out that when we push, we are already only supported on this BR quotient by UR. So that tells me that restriction is actually the same as push forward along this affine thing. And this res star is also push forward along this affine thing. And so Artin theorem tells me that res star, res shriek will give me left T exactness. Res star will give me right T exactness. But we have an isomorphism, right? Because these two were isomorphic. These are the inverses. And so these two things are isomorphic. And so therefore, we get full T exactness. And I'll end there. Thank you.